Hi guys, good morning. Can we start? I think everybody is here, right? Okay, so let me share my screen. Okay, so we completed the first part of equilibrium, that is normal equilibrium, right? So we started with ionic equilibrium, right? So I just gave you the introduction. I told you that we are going to speak about acid, bases, and salts. Majority, not majority. We are going to study about them only, right? So before we move on to the concepts, I said what are the different ways in which you can define acids or bases, right? Say one was Arrhenius theory, the next one was Lowry-Bronsted theory, and the last one is Lewis theory, right? So in case of Arrhenius theory, it is defined in the way that whenever something gets dissolved in water and if it gives me H plus ions, it is called an acid. And same thing, whenever I dissolve something in water and if I get OH minus ions, it's going to be called as basis. And that's about Arrhenius theory. Then I go for Lowry-Bronsted. Lowry-Bronsted talks in terms of protons, right? Whichever is able to donate protons or acids, which are able to accept protons or bases, right? And lastly, when I go for Lewis, it said that whichever is able to accept a lone pair of electron is what is called as an acid, Lewis acid, and whichever is able to donate a lone pair of electron is what is called as a Lewis base, right? Okay, fine. Now that we understood all that, right? Okay, guys. Now, when I speak about strength of acids or bases, right? So we know certain acids are strong, certain acids are weak. Say same goes with bases, strong bases, weak bases. All these things we have, right? So generally, how do you go about it, guys? When I say strong acid versus weak acid, right? Now, how do you generally categorize them? Till 10, you would have studied about it, right? What is the criteria for them something to be a strong acid? Hmm?
It should have a low pH value.
Okay, not that way. If you don't know anything about the pH, right? I give you two acids, like say I give you HCl and I give you acetic acid, CH3COOH, right? So we know HCl is a stronger acid. Why do we say that? Why do we say HCl is a stronger acid? Oh, something is there in the chat. More H plus ions. Yes, makes sense, right? So it's all about how much dissociation is happening, right? Say now if I have an acid like HA, right now it is going to give me H plus A minus. This A minus can be anything. Say in case of your HCl, this A minus is Cl minus, right? Now if it is going to be acetic acid, this is going to be CH3CO minus, right? So like this is the reaction. Now this reaction, how much it goes to completion, right? Say if I take my HCl, right? Say if I have initially say 10 ml of the acid, right? If I had 10 ml of the acid, now you will see that almost all these 10 ml of the acid has given me H plus and OH minus, I mean H plus and Cl minus, right? But if it is going to be in the case of CH3COOH, say if I had on 10 ml initially, right, I am going to get say only 5 ml here, right? I'm going to get only 5. I'm just telling you approximately, right? It depends. 1 second, guys. Right? Say I'll get approximately getting only. Why is it happening? What's wrong? Okay, right. So you can understand the extent of dissociation, right? So instead, all the 10 ml gave me H plus and Cl minus, but out of the 10 ml, only 5 ml was converted to H plus and CH3CO minus, right? So it's all about the degree of dissociation. Like a strong acid is said to be 100% dissociated, right? But a weak acid is only partially dissociated to give me H plus ion and the counter anion, right? Now, this is qualitatively speaking, right, in the sense that we are just telling and not in terms of numbers, but in terms of the extent of dissociation, right? So we will speak about this in detail when like as we move on. But if at all I want to give a number, right, if at all I want to say give a number saying that this is a stronger acid and this is the weaker acid, right? Now that particular term which you used, Rohan, that is the term which you used for quantitative segregation of strong and weak acids, right? Say now we know what is the pH, right? Say pH will be basically the pH of HCl will be around say 1, 2, 3. Like it depends on the concentration, right? So this is for HCl, right? Now if it is going to be for CH3COOH, you'll see that it will be around 3 to 5. This is for acetic acid, CH3COOH, right? So now you can understand as the acidic strength decreases, the pH value increases, right? So whichever is having a lesser pH value is a better acid, is a stronger acid. Now it is going to be ulta in the case of your bases, right? Say pH, like for example, if I have a base like NaOH, right? Now NaOH will have a pH of around say 13 to 15, right? Say now if I have bases like say ammonium hydroxide, this is a weak base, right? Ammonium hydroxide will be having from say 10 to 12, right? So it's a 15 is not possible, actually it's 14, right? Maximum value can be 14. It starts with 0, but some scale will have 1 to 15, but generally it will be from 0 to 14. Okay, right. So this is the qualitative way of analyzing whether the acid is strong or weak. And if you look at the pH, that is the quantitative way of segregating acids and bases. Okay, right, guys. Now this pH concept has to be introduced properly, because we are going to deal only with these pH values throughout this particular part of the chapter, right? So guys, so we say that some acids are strong, some acids are weak. So definitely we need to have some middle ground, is it not? There should be something which is say neither acidic nor basic, or say it can be more what to say, it can be both acidic as well as basic. So we have to have some kind of what to say, some kind of middle ground for us to measure the other substances, right? Say relative to that particular substance, this is a stronger acid. Relative to that particular substance, this particular base is a stronger base. So you need something that's reference point, that middle ground you need, right? So that reference point or middle ground is what is my water molecule, right? So from water molecule, everything you see, all the pH values, all the qualitative analysis is really going to be dependent on this particular molecule, water. Okay, now water is so special because even when you look at the Arrhenius theory, we said that if we dissolve something in water, it gives me H plus on all that we speak, right? So H2O is actually going to play a very, very major role in actually, I would say, the concept of pH, right? And about the strong and weak acids and bases, right? Now let me look into how is it that H2O can be used as the reference material, right? Or say the starting point or whatever it is, right? Fine, we'll move on. So H2O, what is going to happen? As I told you, this H2O can act as an acid, right? Can act as a base. Or before you move on to look at this, people, right? Say if I have HCl with me, or any acid for that matter, right? Now this acid is capable of giving me H plus. It's not like directly you give HCl and the reaction you write is H plus plus Cl minus. This is actually not fully correct. Okay, now why is it like this if you ask me, right? So yeah, HCl is an acid, I don't deny it, but for it to give me H plus, right, there should be something along with this to accept the H plus. Please understand, right? As long as you do not have anything to accept the H plus, this HCl cannot donate H plus, right? So like something can be regarded as an acid not only with respect to say it can give me H plus, right? But it also depends on if there is something in the solution which will be able to accept the H plus. Then only this reaction goes to the forward direction. As it not, then only it will keep on moving in the forward direction. If not, if there's not enough substance to accept the H plus, now the reaction is going to stop them somewhere in between. Okay, right. Now, like I'll give you a sense of this. Say, for example, if I have HCl, if it reacts with H2O, right? Now, what is going to happen? Now, we know that this is going to give me H plus, right? Now, obviously, water molecule in this case is going to act as H plus acceptor. Please understand that, right? HCl is going to give you the H plus donor. I would say I can even write it here, donor, and this is my acceptor molecule, right? Now, what is going to happen if this donates H plus to this, right? So can I say H2O plus H plus will give me H3O plus, right? And what is remaining in HCl? H plus is gone. You write Cl minus. Okay, this is the exact way of writing, right? So you should not we generally write it as this, but it's understood that there's going to be water molecule, and now you understand, right? Why in Arrhenius theory they specify saying that you have to dissolve that particular substance in water only, right? Because you will be it's not exactly H plus, it is actually going to be this H3O plus ion dissolved as hydronium ion. H3O plus ion is hydronium ion, and that is responsible for the acidic nature of HCl, right? Now, same way if I take a base, right? So if I take a base, NaOH, for example, right? Now, again, we write it as NaOH gives me Na plus plus OH minus, but again, that is not the way you write it, right? So obviously, now this is going to act as, now see, we can talk in two ways. I can talk in the way that it is going to donate OH minus, but that's not how we're going to talk about it. Now, this one is going to be a H plus acceptor, right? Please understand, guys, if there is going to be an acid-base reaction, right? Now, what do you mean? Now, in this case, how can I regard this as an acid-base reaction? Obviously, there is a donor, there is an acceptor. Donor acceptor is always with respect to H plus, right? So donor H plus donor, H plus acceptor. Now, in this case also, I'm going to have H plus donor and H plus acceptor. Obviously, the base is the one that is going to accept the proton. What next theory? What is the next theory? Next theory is Lowry-Bronsted theory, right? So this is going to be the H plus acceptor, and in this case, water molecule is going to act as an acid, right? Water molecule is going to act as an acid in the sense it is going to be the donor molecule here. Right. So now what is going to happen? Now this OH minus is capable of abstracting a proton, right? So OH minus from this is going to, OH minus from here is going to abstract a H plus from this. Now what is going to happen? If from H2O, if I abstract, what is that? H plus, now what will be remaining? OH minus will be remaining. Right? OH minus will be remaining from water molecule. And what is the other thing? Obviously, Na plus will be remaining, no doubt about it. Right? Na plus will be remaining. And what else? What to say? Right? So now this OH minus has accepted H plus. Now what is going to happen? I'm going to have water molecule also. Okay, hope you understand how this works, right? If you don't understand, it's pretty simple, right? It's, see, now this OH minus is going to take H plus, right? So if what is remaining from water molecule is OH minus, and this OH minus and the abstracted H plus is going to form water molecule, and what is remaining is Na plus. That's it, right? So now you understand how bases are giving me OH minus. It's actually not coming from NaOH. It's actually coming from the process of abstracting a proton from H2O to form OH minus. That's how it works. Okay, now these two are the exact ways you write acid dissolved in water, base dissolved in water to give me H3O plus and OH minus ions, right? So now you understand the importance of what this particular molecule plays here, H2O, right? Okay, moving on. Now that we understood why water molecule is so important, right? I told you that water molecule is going to be the base or say the reference point for all the pH values, right? Now there is a small, I would say, how history developed pH, right, is actually based on water molecule. We'll see how it goes, right? So now, guys, if I take two now, okay, now before that point, I want to tell you one more thing, guys, right? Say now in this case, H plus, we know H2O is not that much acidic. Actually, it's not acidic, not basic. Again, not, but it's not, we cannot say that it is not entirely acidic or it's not entirely basic, because now you see in the reactions, right? If you see in these reactions, you see that H2O is acting as an acid or a base for that matter, right? So these kind of substances are what are called as amphiprotic substances. It's not amphoteric, guys. Amphoteric is for oxides. Like this is called amphi. Oh God. Right? So these are what are called as amphiprotic substances. What do you mean by amphiprotic substances? They can act as H plus donors. They can also act as H plus acceptors. Those kind of substances, even ammonia, no, ammonia will not come into this, right? So these kind of substances are what are called as amphiprotic substances. Okay, right. Now the same reaction, guys, right? Now in, say, assume that this reaction has, okay, now from this, like from this particular equation, right? Now, say this reaction has gone to, assuming that it has gone to 80% completion, right? Assuming that it has gone to 80% completion. Now, same HCl, oops, sorry. So same HCl, if I try to react it with NaOH, right? I know I'm going to have some reaction. I'm going to have water and water molecule and NaCl getting formed. That's okay. Now here what I'm trying to say is that this is going to act as H plus donor and this is going to act as H plus acceptor. So there also you have a H plus donor acceptor. Here also you have a H plus donor acceptor, right? Now the question is, tell me the reaction goes on to completion, right? I mean, reaction goes on, like reaction will come to a conclusion. So say, as you like, tell me the percentage completion in the last case when I had just water molecule is 80. Now tell me, for this molecule, for this particular reaction, will it be greater than 80% or less than 80%? What will be your answer? Hope you understood my question. Last time I put HCl in water, I said that the reaction went on to 80% completion. That's a random number, guys. Right? Now, this HCl, if I put it with NaOH, I know it is going to go, it is going to react and say the reaction percentage completion will be greater than 80% or less than 80%. Tell me. You need not be correct. What do you think? It can just be a guess. It can be anything. Right? So tell me whether it is going to be greater than 80% or lesser than 80%. Okay, let me take a vote. How many of you say it's going to be greater than 80%? Guys, it's just a game. It's not a game, it's just a guess. You can just put your votes. Put the votes in your chat box or open your mouths and just tell me how many of you think it is going to be greater than 80%?
That might be greater, sir.
Okay, one vote for greater than 80%. Anybody else? Anybody else? Everybody has to vote here. You have to say either greater or lesser. Okay, Pranav says greater. So two votes for greater. Abhishek says greater. Okay. Quick, greater or lesser? Is that's the only word you have to say. Okay, Rahul says greater. Okay, Venisha says greater. Okay, 1, 2, 3, 4, 5. Okay, I think how many people I have? Right, I have almost 8 people. I have got only for 5 peoples. Okay, 6, greater. Shruti says greater. Can it have 2 more? Okay, fine. So yeah, yes, guys, your answers are correct. Right now, like the thing is, for the last reaction and this reaction, HCl is common. Right. The only difference is H2O and your NaOH. Right now, the question is which will act as a better H plus acceptor, or say in other words, which is going to act as a stronger base. Whichever is going to act as a stronger base, or in a sense, whichever is able to act, whichever is going to act as a better H plus acceptor, in that reaction, the reaction goes on to more completion, in the sense that this reaction has a stronger base, has a stronger H plus acceptor. So definitely the reaction completion will be greater than 80%. No doubt about it. Right? Okay. So what I understand is, so when I told you that this concept of what is that, the amount of dissociation, H plus giving me H plus and Cl minus, if I incorporate this here and here, right, what do I see is in this reaction, when I have H2O, I am going to have a particular strength of the acid, particular strength of HCl, right? But if I have the HCl reacting same concentration, everything same, but it goes on, when I react with the NaCl, I'm seeing that HCl is going to act as a better acid, in the sense that it is going to act as a stronger acid. Right. So that does this mean that HCl is going to have different strengths in different acids? I mean, different reactions. The answer is no. It's pretty confusing, right? If you put H2O, I am getting one strength value. If I put NaOH, I'm getting another strength value. Say if I put say I make it react with ammonium hydroxide, NH4OH. Say I'm going to get another value. Right? So in this case, it will be greater than 80% for sure, right? But again, it will be not as much as this, right? So that means in this case, HCl will have again a different strength, different value, right? So to avoid all these confusions only, guys, right? So we are going to have some standard substance, and that is going to be water. Okay, because when I put HCl in different basic solutions, when a different H plus acceptor solutions, right? So I'm going to have different strength value. Right. So to avoid all this confusion, I will just take water molecule and I decide the number. And based on that particular number which I have derived, then I will be using that values only for HCl, that values only for NaOH, again, that values only for NH4OH, because everything else is going to get derived from water molecule. Hope you understand. Then it makes it a universal, say, same thing everywhere kind of thing. Right? Okay. Now we'll move on, guys. Now you really understood why water is very important. Right? Fine. Now moving on. Right. Now, as we just discussed, water can act as H plus donor as well as H plus acceptor, right? So now, generally, how do we write a reaction? If at all I want to write dissociation of water molecule, right? So now, how do I write it generally? I write it as, again, right? H2O will give me H plus OH minus, right? So this is how we generally write it, right? But again, we know that we should not write it. Now, one reason is obviously you should have a H plus acceptor and a H plus donor. And second thing is this H plus ion I generally write so many times I write, this is really not going to exist in solution. Right? It is really unstable that you really cannot find H plus ion in the solution. Right? So what is a better way of writing then? Right? So better way of writing would be to take two water molecules, right? Two water molecules, one say is going to act as H plus acceptor and the other is say going to act as H plus donor. right? So now what is going to happen? I can write it like this. Say if this is the molecule is going to act as donor, H plus donor, I can take anything, guys, both are H2O molecules, and say this is my acceptor molecule, right? So the donor from, if I remove H plus from the donor, what will be remaining is OH minus, right? And if I add H plus to this, it is going to become H3O plus. This is the correct way of writing. Okay, this is wrong. This is the correct way. Two water molecules, one is going to act as H plus donor, the other one is going to act as H plus acceptor. Is that okay? Right now, for this reaction, guys, for this reaction, if I write my equilibrium constant, okay, if I write the equilibrium constant, now since it is water molecule, I'm going to give some special name to the equilibrium constant. It's going to be called as Kw. W represents water. Okay, now this Kw, how will I write? It will be H3O plus concentration into, again, product concentration by reactant concentration divided by OH minus concentration divided by what? Divided by?
Reactants concentration.
Yeah, what is that here? Should I
H2
put
into H2O.
Should I put H2O? H2O is H2O. I know it's a liquid. So what is the value which I should put here?
1, sir.
Exactly, right? So you don't have to include H2 at the denominator because H2 is a pure liquid. As we already discussed so many times, you don't have to include pure solids and pure liquids into the equilibrium, what is that? Equilibrium constant formula, because their active mass is 1, right? So this is the value. This Kw is going to be equal to concentration of H3O plus into concentration of OH minus. Very simple, right? Now, this Kw can actually was experimentally determined. Okay, through some technique, you don't have to know the techniques, again, really out of the scope of your books, right? So through some methods, right, they found out this Kw value at 25 degrees Celsius. Obviously, when I have temperature increase or decreasing, this Kw also will change. We know that your equilibrium constant is temperature dependent. We even saw how it may behave depending on whether it's exothermic or endothermic. It is going to change anyways, right? So at 25 degrees Celsius, this Kw value was measured, and the value was measured to be equal to 10 to the power minus 14. Okay, now you have to remember this value, guys. Okay, well, if I ask you what is the Kw acid, what is that? It is called water dissociation constant. Okay, this Kw is what is called as water dissociation constant, right? So the Kw value for water at 25 degrees Celsius was found to be 10 to the power minus 14. You have to remember this value, right? Fine, Kw is 10 to the power minus 14. Now, how would they have arrived at this? It's pretty simple. Like, how would they arrive at the not about the method? I'm talking about the mathematics here. Okay. Now, if you look at this, guys, I have H3O plus ion, I have OH minus ion. Now, from the stoichiometry, right, I can easily say that whatever is the concentration of H3O plus, that exact same concentration will be the value for OH minus ions also, because both are coming from water only, right? So stoichiometry says if I have 1 mole of this, I will have 1 mole of this, right? So what I can understand is this Kw value would have been 10 to the power minus 14 if H plus or H3O plus concentration was 10 to the power minus 7. Right, this H plus concentration was 10 to the power minus 7. Right, and this OH minus concentration was also to be 10 to the power minus 7. Right, okay, only then I'll be getting a value of 10 to the power minus 40. And why why not any other value? Why I cannot put 10 to the power minus 6 and 10 to the power minus 8? Because from the equation I can understand the stoichiometry. I can understand that H plus concentration and OH minus concentration should be same, right? So obviously the only way to get 10 to the power minus 14 is when you have 10 to the power minus 7 for H plus, 10 to the power minus 7 for OH minus, right? Now what we can do is now we go for, I'm going to introduce you the concept of pH, right? Now pH is a formula, right? pH is equal to negative log of H3O plus, or say generally they write only H plus, right? But to be exact, we write it as negative log of concentration of H3O plus ions. Okay, and guys, you will be using a lot of log terms here. You have to be good with logs, right? Not like looking at the log books and finding the value. No, I'm telling about the mathematical operations you can do on logarithms. We already discussed it, right? So yeah, so this is how, this is what is the pH formula. Very, very famous formula, right? pH is equal to negative log of H3O plus ion, right? And guys, if I want to find what is the pH of this particular water molecule, right? Now, what do you see here? What is the concentration of H3O plus ion? I find that the concentration of H3O plus ion is 10 to the power minus 7, right? So if I substitute the value in this pH equation, right? So if I substitute the value, so you can see the concentration of H plus is 10 to the power minus 7, right? So pH of water at 25 degrees Celsius, obviously it's again temperature defined, is equal to negative log of, what is the value? Value is 10 to the power minus 7, right? So we know how it works now, guys. Like when I, okay, what is the value? Tell me, what is minus log of 10 to the power minus 7? What is the value? What is the value of log of 10 to the power minus 7? Minus log of 10 to the power minus 7. Okay, I think you should have forgotten. So remember the operations, guys. If I have log log of some log of say a to the power b, how can I write it now? Tell me. Log of a to the power b, how can I write it? Log of a power b, how can I rewrite it? Anybody remember or
B
nobody
log
remember?
A.
Correct. Thank God. Right. So you have to put this b here. Right. So I can write this as b log a. Guys, please remember this. These logarithmic operations are going to be very, 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 very useful. Right. Okay. Now, if I apply this particular thing, what I did here, what will happen? So basically, I have log minus log of 10 to the power minus 7. Right. So if I bring the minus 7 that side, minus and minus gets cancelled. So basically, I will have 7 log 10. Right. So 7 log 10, what is log 10 value? Anybody remembers? What is log 10 value? Okay, please remember, guys, log 10 value is 1. Okay, log 10 value is 1. It's not 10 power 1, please don't. Okay, log 10 value is 1. So 7 into 1 will become 7. Right? So what is the pH of water at 25 degrees Celsius? pH of water is said to be 7. This is the reference point, guys. Right? This is how we say that water is neutral. We know whenever something has a pH of 7, we say that it is going to be neutral. Isn't it? Neutral in the sense the concentration of H plus and the concentration of OH minus are going to be same. Only then I will be getting a pH value of 7, and water molecule at 25 degrees Celsius is neutral because it is going to have a pH value of 7. And this is the reference point. And whichever is below 7 is going to be called as acid, and whichever pH value is greater than 7 is going to be called as a base. This is the reference point. Okay. Now, please, the only thing I'm worried about, all the things that I've understood, the only thing which I'm worried about for you is about the log values. Log values in the sense, the log mathematical operations. Okay. So you don't have to you at least remember log 1 is 0, right? Log 1 is 0 and log 10 is 1. Please at least remember these two values. Other things you can look at the log books. Even for this, you can look at the log books. But again, you want to spend 2 minutes on taking out the log book, looking at the value, really not worth it. Okay, log 1 value is 0, log 10 value is 1, and this is a one operation which you have to remember. Another operation which you can remember is log of a into b, log of ab. If I have a multiplication, I will be able to write it as log a plus log b. Please remember this also, right? Whenever I have multiplication of two things inside, I can just open up the log and write it as additions, log a plus log b. Same way, if I have log of a by b, I can write it as log a minus log b. Okay, so only these things I wanted to remember. Log 1 is 0, log 10 is 1, log of a power b, I can write it as b log a, log of ab, I can write it as log a plus log b, and log of a by b, I can write it as log a minus log b. That's it. This much, if you remember, you can go for this chapter. Easy. Rest of the things are only formulas and concepts. That's it. Okay. So any questions, guys? Any questions till now? We just proved through mathematics and through experiments that water is neutral, and that's the base value. So pH of water at 7, pH of water at 25 degrees Celsius is 7, right? And one other thing I want to remember from this is about the Kw value. Kw for water at 25 degrees Celsius is 10 to the power minus 14. Only from that I'll be able to derive the pH. Please remember that, right? So Kw value we have to remember, pH value of water is 7, and the pH formula we have to remember, and the log operations. That's it. Okay, right? Cool. Now we'll move on. I think we have to now make a page, see where we started. We started with what are acids, what are bases, strong acids, strong bases, why water, Kw for water, pH of water, and the log calculations. That's it, right? So move on, we'll move on. Right, okay. Now we'll speak about, again, acids and bases only, right? But again, you say the pH is not the only way by which we'll be able to quantitatively speak about the strength of an acid or a base, right? There are other ways, right? There are other numbers which can be used to determine, not determine, to quantitatively speak that particular acid is a strong acid or weak acid, or at least to compare two different acids, and they say that, okay, this is a stronger acid, this is a weaker acid. So for all those things, we have so many other, what is that? So many other numbers that is going to help us. Okay, fine. So now we are going for, like, and guys, since we are speaking on, like, you can understand from the previous part, we spoke only about reversible reactions, right? Or in the sense, we will speak about reactions which are not that fast, right? We will speak about reactions which are pretty slow, right? Okay, so what I'm trying to say is in this area, like in whatever you're going to study, we are actually going to study only about weak acids. Okay, we are going to study only about weak acids, right? So we are going to study only about weak acids. Now I'll tell you why are we not studying about strong acids. Okay, now it's the same reason. Say if I have HCl, and if it is going to give, again guys, this is not the right way of writing it, but still, right? So when I have HCl, it gives me H plus and OH minus. Now you can understand that this concentration at a particular point of time will become 0, right? So again, what we had in case of your irreversible reaction, and I told you that irreversible reaction cannot be is not mathematically useful because something is becoming 0 at the end of the reaction, right? Same goes with your strong acids, strong bases also, right? You will not be able to give a proper number, or you will not be able to involve them in the mathematical calculations, because one of the term at the end of the reaction is actually, at least we assume that it is going to become 0. Now, even though it is going to be 0.000 something, right? Approximately, we can say that it is going to become 0. And that is the reason why we don't speak, we don't generally talk for strong acids. Strong acids, we can talk in terms of pH. That's wonderfully useful, but not really the methods in which we are going to see now. Is it okay? Right? Fine. Cool. Moving on. Right. Say assume that I have a weak acid, right? So weak acid, say the weak acid we are going to use is HA, some acid, right? So now this will give me, again, don't start. Okay. So I have an acid HA, and this is going to give me H plus A minus. Okay. Now, now it's like for this reaction, right? For this reaction, I can actually write the equilibrium constant, is it not? Now, but for this reaction, I cannot write the equilibrium constant. Why I cannot write the equilibrium constant? Again, the same reason that the concentration of HCl is actually becoming 0, right? So we will not be able to write the equilibrium constant here. But here for this, I can write the equilibrium constant because this is not going to become 0 at any point of the reaction. Even though the reaction has reached equilibrium, say this is an equilibrium, this is a reversible reaction, right? This is not really going to become 0. Right? Okay. So anyways, now I'm going to write the equilibrium constant, guys. Now that equilibrium constant, I'm going to call it as Ka. Now Ka represents acid dissociation constant, right? This Ka, whenever you have an acid dissociation happening and you write the equilibrium constant for that, it is going to be called as acid dissociation constant. Right. Now, how will I write this here? It will be equal to concentration of H plus into concentration of A minus divided by concentration of HA. Is it not? Right? Concentration of, this is the products by reactants. Very simple. Concentration of H plus by concentration of A minus divided by concentration of HA. Right? Okay, now there is another way of writing it. This is pretty simple. With that we understood, right? Now let me write the reaction again, right? So I have, maybe let me make some space. All right, say again, write the reaction. I have HA giving H plus A minus. Right. Say assume that I started with some 1 mole or the concentration is 1 initially. At time, I'm trying to draw the equilibrium table, guys. Right. At time t is equal to 0. Right. I have 1 and 0, 0 here. No, the reaction wouldn't have started yet. Right. So now when I reach equilibrium, right, say now I'm going to have some alpha moles reacting here. Instead of X, I just write alpha. There is the, right? So now what would I have got? So 1 mole gives 1 mole and 1 mole. So alpha moles, if it have reacted, it will give me alpha moles and alpha moles of H plus and A minus. Right. Now say this, okay. Now this alpha is what which you're talking here, right? So for 1 mole or say for 1 m concentration, right, how much is reacting, right? That is what is alpha, right? So this alpha, I'm going to give it a name. It is going to be called as degree of dissociation. Is it not? Degree of dissociation, the extent of dissociation, right? Depending on the alpha value only, I say that this much dissociation has happened. Let's say, for example, if alpha value is 0.5, that means what? It has been 50% dissociated, right? And say if I tell the alpha value is 0.3, that means what to say? That means the reaction has gone up to 30% completion. Hope you understand, right? This alpha is what is the degree of dissociation, right? So then obviously the alpha value can be between 0 and 1, right? And if it's a 1, if it's totally undergoing, that means what? This represents 100%, this represents 0%. Okay, now the alpha value can be between 0 to 1, and it's called as degree of dissociation, and depending on that we can say that how much it has gone to completion, right? So obviously stronger acids will have alpha value 1, means obviously if I put 1 again here, it is going to become 0, but we will not talk about that case because it is not going to be useful. But for weak acids, for any weak acid, right, definitely alpha value will be less than 1 and will be greater than 0. If it's greater than 0 means what? The reaction it's not an acid at all. It is not going to give me any H plus and the counter anion. Okay, right? So this is what I wanted to tell you. Right now, this is for 1 mole, guys. Right, this is for 1 mole, or say the concentration of 1 m right? So what if the concentration was some C, some concentration C I had, right? Say now instead of this 1, what I do is I just multiply this by C. So some concentration is what I have. So again, this also can be multiplied by C. This again multiplied by C. This again multiplied by C. So because we did everything for 1m, right? Say if it is going to be for 2m or 3m or 4m, I just multiply that particular number here. Okay, so now what I have is C into 1 minus alpha, C alpha, and C alpha, right? Okay, now if I write the Ka value now, right? Now in terms of the C and alpha, how will I write? It will be C, it will be C alpha into C alpha divided by C into 1 minus alpha, right? This is what is my Ka value, right? So now moving on, if I just do it properly, so I can write Ka as C squared alpha squared divided by C into 1 minus alpha, right? So I can cancel C and one of the things. So this is the last equation, C alpha squared divided by 1 minus alpha. So the C is what is the concentration of the acid, right? And I know what is alpha. Alpha is degree of dissociation. Okay, whatever. Say if I tell you there is 2m concentration of H, say CH3 over H, right? And the alpha value is say 0.5, and I ask you to find the Ka value, you will be able to easily find it. C and alpha value are given, you substitute and get the answer. Okay, right? Fine. Now I will be able to slightly remodify this equation. Right, I will be able to slightly remodify this equation if alpha value is very less than 1 compared to 1, right? If this value, the alpha value is very less, right? That means the alpha value is like 0.003 or something like that, right? Now I will be able to rewrite this equation in a more simpler form. It's equal to Ka is just equal to C alpha squared. Now why 1 minus alpha? If alpha value is almost 0, 1 minus 0 will become 1, right? So what will be remaining is C alpha squared. Okay, so sometimes, not I would say most of the times we'll be using this only, right? C alpha squared. But again, I'll tell you when to use when to use what. When you go for problem solving, then you'll understand when to use this one and when to use this one. Okay, but again, this is a very simpler way of doing it. From this, I can derive a lot of other stuff. I can derive about the pH. I can derive about so many other stuff. All these things can be done, right? So you have to remember Ka is equal to C alpha squared divided by 1 minus alpha, or I can even write Ka as just C alpha squared. What is the time? We have time, right?
The doubt, sir.
Yeah.
So in denominator, if you're considering alpha as 0, sir, and even in numerator...
No. We're not considering it as 0, right? What we are considering is that alpha value is very less than 1. That's what we are considering. Okay, so if we consider 0, then there is no point in talking about this, right? So when I say the alpha value is very less than 1, 1 minus that particular very small value will still be 0.999999 something, right? So we take it approximately this value as 1 itself. That's the only thing we are doing. We are not assuming that alpha value is 0. No, that we are not doing. If we assume this value also becomes 0, then that doesn't make sense. Right. So what we have to understand here is that the alpha value is very less than 1. That's what we can understand.
So okay. That means even the numerator will have a very small value.
Yeah, let it be. Even if the numerator is of 10 to the power minus of something, some 7 or 8 or 8, whatever, it doesn't matter. Right. It will actually be a very small value. Ka for weak acids will actually be a very small value. Yeah, that's true.
Okay, sir, understood.
Right. Okay. Right. Now, moving on, guys, there are a lot of other things we can do here, right? So with this, with the help of K alpha squared, we can actually do something, right? Now, if you look at this, guys, right, if I want to find the pH from this, now please understand, first we have to locate what is the concentration of H plus ion. If I know what is the concentration of H plus ion, I can just put it in the formula, right? Negative log of concentration of H plus ion, right? So what is the concentration of H plus ion? I can easily see in terms of C and alpha. Like you can see, this is the H plus, and this is the equilibrium concentration of H plus, right? Okay, so now if I want to know the pH value, how will I write pH? Again, pH will be negative log of H plus ions concentration. Okay, now we just found out that the H plus ion concentration is C alpha, right? So for an acid, I can even write pH as negative log of C into alpha. Simple, right? So now it's pretty easy, guys. Now I can even have another kind of formula. This formula you can remember. Right? So this is for an acid, right? In terms of concentration of the acid and the degree of dissociation, we can find the pH, right? Now, what I can do is, if I just bring this equation, if I use this here, now what I can see is alpha, I can write it as Ka by C, right? Root of Ka by C. Now here from this, right? Alpha value will be equal to root of Ka by C, right? So I can even put that there. Okay, so if I put that there, okay, pH will become negative log of root of Ka is there, and root C, and this root C will get cancelled. So I can even write it as one root will be there. Okay, it will be root of Ka into C. Am I right? C alpha, alpha is root of Ka by C. Okay, this is root of Ka by C, and there is one more C. So roots, this will be root C and will be root Ka, correct, right? So this also is correct. Right? So you can remember, if you remember either one of them, say if you remember just this cell again, you can derive this, right? Because you know Ka is equal to C alpha squared. So depending on what is given to you guys, depending on whether Ka and concentration are given to you, or depending on whether concentration and alpha are given to you, you can use either of the formula to find the pH, or it's a you whatever you want to do, you can just do it, right? Because you know this formula, right? This formula, pH formula, and this you can easily write if you just look at the equilibrium table. Equilibrium table, I can easily see, where is it? Here, right? Equilibrium table, if I easily see, this is the concentration of H plus, right? Okay, now there is one more last thing I want to tell you, right? Now we have something called as pKa. Right, we have something called as pKa, right? So guys, please remember, whenever you put this P behind anything, right, when you say pH, it is negative log of concentration of H plus, right? So there is also something called, oh, I forgot to tell you that. So there's something also called as POH, guys, right? So POH is again very similar to pH. It's nothing but negative log of concentration of OH minus ions, right? Negative log of concentration of OH minus ions. So what do you see? Like now, H plus means H plus concentration, OH means OH minus concentration. Now this P always represents this negative log, right? So same way, if I write P Ka, for P it is negative log, right? And for Ka, it is going to be just Ka, right? H plus means H plus, right? So negative log of Ka is what is called as pKa. Okay. Now, fine. Now, if I want to determine whether the acid is strong or weak, right? Now, please remember the strength of an acid is directly proportional to the Ka value. Obviously, more and more is the equilibrium constant, more and more will be the forward direction, and more will be the strength. That is one thing. And if I talk with respect to pKa, strength is inversely related to pKa, guys. Please understand, just like how I have pH, lesser the pH, more the strength. Same way, higher the pKa, lesser the strength, or opposite, whatever, vice versa. Right? So this you remember. Not remember, it's pretty logical. If you look at the values, you can easily put the values and check. Okay, so strength is directly proportional to the Ka value. Strength is inversely related to the pKa value. pKa is nothing but negative log of Ka, and there is something also called as POH, that is negative log of OH minus ions. Right, guys, this much explanation will not be given in your textbook, so it's if you have taken notes, it's really helpful. If you have not taken notes, please go watch the video again and take notes. Right? Okay, I think I'll stop with this for today, guys. Right? Any questions you want to ask?
Could you just repeat that strength part again?
Yeah, so okay, what I'm telling is, so now from the equation itself, you can just, if you go here, right? So Ka value is this, right? So Ka value is basically, or I can even go to this part, right? So Ka value, you can see it is directly proportional to the concentration of how much ever H plus concentration is going to come, isn't it? So obviously more and more H plus concentration will come when this reaction goes on to more and more in the forward direction, isn't it? That means more and more dissociation is happening, right? So obviously that's how we see the strength. More and more is the dissociation, more and more is the strength of the acid. So more and more dissociation will happen, and then I'll have more and more H plus ion and more amount of Ka. That's why we say that strength is directly proportional to the Ka value. Say if I have Ka value of 5 and 10 for two different acids, definitely 10 is a stronger acid, 5 is a weaker acid. Right? And obviously, when you look at the pKa, it is negative log of Ka. It's just mathematics. Now, if you just put the values 5 and 10, right? We already know 10 is stronger. This will have a lesser pKa value than this, right? So that means what? This will have, say, pKa of 2. This is pKa of 1. And obviously, this pKa 1 is going to be greater. Okay, because this is a stronger acid. That's how it is. Like the mathematically, that's how it works. That's it. Understood?
Okay, sir, understood.
Right? Any other questions, people?
Sir, I have one more, but it's from the previous class.
Yeah, tell me.
Sir, in that 1 minute, sir, in that Arrhenius thing you told, sir, in that we use only gases or even solid and liquid in O2, H2O.
No, that is anything for that matter. Anything, gas or liquid or solid, whatever it is. If I dissolve in water, if it gives me H plus, it's an acid. That's it.
Okay, sir. Understood.
Okay, right? But generally, it will be only liquid form. But yeah, HCl will be available in the gaseous form, but not other acids like H2SO4 and all. You cannot see it in gaseous state. You will generally see it only in liquid state. But again, mostly it will be aqueous state, because it's like the naturally also, if you're going to derive H2SO4, you will find that it will have some amount of water present naturally itself, right? So yeah, but yeah, generally it can be solids, liquids, or gases to be dissolved in water. It doesn't matter, right?
Okay, sir.
So guys, right, understood. Okay, so any other question? Anybody want to ask? Right? So you can understand, right, how many formulas we have, how much calculations we have to do when I go for problem solving, right? You really have to follow it very nicely. Okay, so I know this, and obviously this is the last chapter for physical chemistry, and we have three more chapters, and after this, there's no more calculations on the last chapter, which has calculations. Is it okay? Right? Fine, guys. Thank you so much. We'll meet again day after tomorrow. Thank you.
Thank you, sir.
Yeah.
Thank you, sir.